Hello everybody, Namaskar. In the previous lecture I have discussed about the control of a vapor compression refrigeration system. So apart from the control of a vapor compression refrigeration system, the design and simulation of the refrigeration system is also a important aspect for any refrigeration system. So in this lecture I will discuss the simulation for a refrigeration system. So basically what is happening, if you start any refrigeration system, that may be the household refrigerator or in air conditioning system. So depending on the outside parameters like the environmental conditions and also the design of a refrigeration system, based on that after some time that system will come into a steady state condition, and at the steady state conditions means at this condition the mass flow through all the components of the system that will be remain same. So that is basically called the balance condition of a refrigeration system. So any refrigeration system at the steady condition, that is coming to a balance conditions. So that means the heat mass flow rate in the compressor as well as the mass flow rate in the expansion devices, both will be same. So basically the different component of a refrigeration system like the compressor, condenser, expansion device and the evaporator, all are basically interdependent. So that's why at the balance condition we will get the same mass flow rate in both the compressor and expansion devices. So now if you change any type of external parameters or maybe the internal parameter, then you will see that the conditions for all the component will be changed because all the component are interdependent. Then you will see that the system will become again coming to the steady state condition, that means for the another balance condition that will achieve. So that for any external parameter or any influential parameter on that system and for a certain design, we can calculate the balance point for a refrigeration system, or we can say that for the given design of a refrigeration system we can get some, or we can evaluate a balance point for certain external parameter. Okay, so that balance point of a refrigeration system, that can be, we can evaluate by the graphically or the mathematically, that means by using the simulation of a whole refrigeration system. So where we will want to get the balance point for by the graphically. So for this case basically what is happening, what is basically done, that we can test the different components separately and we can make a performance chart for the different components. So we can draw the same quantities in x and y axis, and for a different performance of, or the, if you draw the behavior or the performance variation for the different component, then we will see that we can get some cross point or balance point based on that individual performance. So that performance may be based on the maybe for the compressor and expansion device, or maybe for any combination of the two parameters. Okay, so we can also make the balance point by using the individual performance of the compressor and expansion device, or maybe the compressor and condenser. So for example, in this figure we have plotted the two performance of a two important component of the system. One is the compressor and another is the condenser. So if we change for any given system, or the given design of a system, if you change the evaporator temperature and condenser temperature, then how the mass flow for a certain system or certain component, or based on that component the capacity, how the performance parameter is varying, that you can draw in a figure. So in this figure you can see that we are basically measuring the capacity, then that capacity we can plot it with respect to the or we are evaluating the capacity. So that evaluated capacity that we can draw with respect to the evaporator temperature and condenser temperature. So x-axis is the evaporator temperature. So for the defined condenser temperature, like the condenser temperature of 30 degrees centigrade, condenser temperature of 35 degrees centigrade, and condenser temperature of 40 degrees centigrade. So for defined condenser temperature and for the defined evaporator temperature, if you measure the mass flow rate of the through the compressor, then based on that mass flow rate we can evaluate what is the capacity. So if you draw the behavior of capacity with respect to the evaporator temperature at the different condenser temperature. So in this figure, that the solid line, this is basically represent the capacity change with respect to the evaporator temperature for the different condenser temperature. So similarly, if you measure or if you evaluate the mass flow rate to the condenser, and based on that mass flow rate if you evaluate what is the capacity, and if you draw the capacity versus the evaporator temperature for the different condenser temperature, then those are basically represented in this figure in case of the dotted line. Okay, so dotted line are represented basically the capacity variation with respect to the evaporator temperature, condenser temperature, and solid line represent the variation of capacity with respect to the evaporator temperature and condenser temperature. So but at the balance condition, the capacity based on the compressor measurement or based on the condenser measurement, so both should be, for both case these values should be same, because the capacity is a parameter. So if you measure or if you evaluate the performance based on the any parameter or any component performance, so the capacity that should be same at that case. So that means the intersecting between the similar line in case of compressor, in case of condenser, that line should be touched cross at a point, and in that intersecting point is basically represent the balance point for that evaporator temperature and condenser temperature. So that means for both the cases, the mass flow rate if you measure for the compressor and condenser, both will be same. So that's why you will get the same capacity. So at the balance condition, the capacity should be same, that means the mass flow rate also should be same for the both the component, and that is basically represent the balance point or the steady state condition or steady state point or the operating parameter or performance parameter at the steady state condition if the all the other parameters are remain same. Okay, so like for example, the point A, that is basically represent the operating point or balance point for the corresponding evaporator temperature and the condenser temperature of 30 degrees centigrade. Similarly, the B is represent the corresponding evaporator temperature and condenser temperature 35 degrees centigrade, and the C is represent basically the balance point for the evaporator temperature, that corresponding evaporator temperature and the condenser temperature of 40 degrees centigrade. So this has been basically plotted for the fixed compressor speed and condenser water flow rate and the water inlet temperature for the condenser. So A, B, C are the balance point for the three different combination of the evaporator temperature and condenser temperature. That means if you join A, B, C, so the any point in the line, okay, any point on the line, so that is basically represent the balance point for the corresponding evaporator temperature and condenser temperatures. For example, in between A and B, if we assume this is the point, so this will be the balance point for the corresponding evaporator temperature of this, and this condenser temperature should be in between the 35 degrees centigrade, 30 degrees centigrade. So the in between that temperature, condenser temperature, and for this evaporator temperature, this point is represent a balance point for the refrigeration system. Okay, so these type of graphical methods we can use to evaluate the balance point for a refrigeration system. So we can measure the performance of any two component of a refrigeration system, and if you plot this performance of these two individual component on a single graph, okay, so we can easily see that what is the intersecting point be in between the behavior at the corresponding same operating conditions. So that intersecting point will basically represent the balance point for this system. So this is the general methodology to calculate or evaluate the balance point graphically. So let's say another example we can take in this slide. So for this case, basically I have plotted the mass flow rate or cooling capacity. So with respect to the evaporator pressure, okay, with respect to the evaporator pressure. So with respect to the evaporator pressure, we can see that what will be the mass flow rate to the compressor and what will be the mass flow rate to the capillary tube if we change the evaporator pressure. Let's say the condenser pressure is fixed. So for this case, condenser pressure is fixed, we are basically changing the evaporator pressure. So we will see that for a certain condenser pressure, we will see the behavior mass flow rate of the mass flow rate with respect to the mass flow rate to the compressor with respect to the evaporator pressure. So in this figure, this m dot c, so this line is basically represent the mass flow rate to the compressor with respect to the evaporator pressure. So according to this line, we can see that as the evaporator pressure will increase, then the mass flow rate to the compressor that will increase. Similarly, if you see what is the mass flow rate to the expansion tube, then we will see that as the evaporator temperature will increase, so that will basically decrease the pressure difference in between the condenser and evaporator. So as the pressure difference will decrease, then you will see that the mass flow rate to the capillary tube that will be also decrease. So that means the mass flow rate to the compressor that will increase with the increase in pressure with the decrease in pressure ratio, and the for the capillary tube that will decrease with the decrease in pressure ratio. Okay, mass flow to the capillary that will decrease with the decrease in pressure ratio. So in this plot, you can see that the both line are intersecting at a point, this point. So that means that this point is basically the balance point for this evaporator pressure and that corresponding condenser pressure. Okay, so now if we use the evaporator pressure above this or below this, then what will happen? So if we use the evaporator pressure below this, so that means let's say the line C. Okay, so the point line A, this is basically represent the balance point. That means if the evaporator pressure is equal to for the point A, so that is the balance point. Now if you maintain the evaporator pressure that is corresponding to the point C. Okay, so for the corresponding for point C, you will see that the mass flow rate to the compressor that will be lower as compared to the mass flow rate to the capillary tube. So what will happen that refrigerant that will be stored in the evaporator. So that is basically called the flooding point. Now the opposite case, if you consider a evaporator temperature at point B, so correspondingly you will see that the mass flow rate to the compressor that will be higher as compared to the mass flow rate to the capillary tube. So for this case, the extra mass that will be stored in the condenser. So that means the evaporator mass that will be reduced and condenser mass that will increase. So that condition is called the starving condition. Okay, so that means if there is any mismatch in between the compressor and capillary tube mass flow rate, then either the extra mass will be stored in the condenser or the extra mass will be stored in the evaporator. So the balance of the system that will be, so there is no balance in between the flow in the compressor and expansion devices. So this has been clearly explained here, that what will happen with the respect to the load. Okay, so let's say for example, if the load will increase, then as the load will increase, then the evaporator pressure that will be rises from the A to B. Okay, so at the B point, basically the mass flow rate of the compressor that will be greater than mass flow rate of the expansion devices. So what will be happen, the extra mass that will be stored in the condenser, so that's why the condenser pressure will increase. Condenser pressure will increase, then as the condenser pressure will increase, then the m dot E, that means the mass flow rate to the expansion device, that will increase, but the mass flow rate to the compressor that will decrease. Thus we will get the new balance point. Okay, so we will get the new balance point for this condition. So that means for the certain load we will get some balance point, and as the load will change, then the change load condition we will get another balance point. Okay, so same thing can be happen if the load will decrease, then your that evaporator pressure that will also decrease, that means to decrease from the A to C. Then again you will see that the mass flow to the that means the mass will be accommodated in the evaporator. Okay, so that means the mass flow expansion mass flow rate that is more as compared to the compressor mass flow rate. So the extra mass that will be stored in the evaporator, so the evaporator pressure will again increase, then we will get a new balance point for that condition. Okay, so for the each load we can get the different balance point, and that is basically the conditions for a steady state operation. So apart from this, the another option that we can use, that is called the simulation technique. So we can use the simulation technique to get the balance point of the system, or to calculate the steady state point of the system. So for the simulations, two type of simulations are generally used for a refrigeration system. One is called the sequential calculation. So for this case, we can simulate the each component. So and then the one component outlet that will be take as a inlet of the other component, then that component outlet will be take as inlet for the other component. So one by one, if you do the simulation and if you calculate what is the outlet condition, then because this is the cyclic process, so that means the at last component, that outlet condition should be equal to the inlet of the initial that the first component. So and that condition should be matched. Okay, should be a match. So by this way we have to do some iteration and to for this matching to get the balance condition or steady state conditions or for the different state point for the steady state operating condition. But in case of simultaneous calculation, so for this type of simulation we will simultaneously solve equations for all the components simultaneously, and then we can do the iteration and we can do the simulation, and ultimately we will get the operating parameters or the state points at a steady state condition or at the balance point. So for the sequential we will do the simulation one by one component, and for the simultaneous calculation we will do the simulation simultaneously for all the components. Okay, so some example I have given here. So let's say for if you consider a vapor compression refrigeration systems, and for that case, let's say for example I am taking in a evaporator that is used for the cooling purpose. So some fluid is cooled in the evaporator, and in a condenser also some fluid or some liquid is used for that cooling process. So for the condenser, the secondary fluid is used, and there is some inlet condition and outlet conditions of that secondary fluid or the coolant. And in case of case of evaporator also, we are assuming that some fluid is going into the evaporator and cool down, and that coming out from the evaporator, and that fluid may be water, air, water, whatever may be. Okay, so for this type of cases, now you have to simulate the system, or you have to calculate the balance point or the different state point for the steady state conditions. So for this case, let's say with the compressor speed that is given, that is fixed, and if the inlet conditions of the external fluid, like the in case of evaporator, if you know what is the mass flow rate of secondary fluid and what is the inlet temperature of the secondary fluid. Similarly, in case of condenser, if the mass flow rate and inlet condition of the secondary fluid is given, then for that condition, for the fixed mass flow rate rotational speed or the speed of the compressor, we have to calculate what will be the different state point. Okay, so for this case we can do the first type of calculation or simulation method, or second type of simulation method. So if you use the first type of simulation method, so for this case we can assume the state point on, then if you do the modeling for the compressor, then we can get what is the outlet condition of the compressor, and outlet of the compressor will be taken as the inlet condition of the condenser, and based on that we can calculate the outlet condition of the condenser, and then that will be taken as an inlet for the expansion devices. Then for the expansion device model, we will calculate what is the state point for that outlet of the expansion device, and then by the simulation or modeling of the evaporator. So for this case we can get the new value of state point on. So now that we can check this new value with the old value of the state point on, and we can do some certain sufficient number of iteration to merge the old value and new value, and we can get the steady state condition or the different state point for the steady state condition, or the balance point for the given outlet conditions and the compressor speed. Thank you.